Hi everyone, today we're going to learn how to find the wholes and asymptotes of a rational function. We know that a line that continuously approaches a given curve but does not meet it at any finite distance is called an asymptote. For example, here I have an asymptote, the vertical asymptote, and this is my graph. This asymptote is trying to get close to the curve as much as possible but does not meet it at any specific point or any finite distance. So this is called an asymptote. A whole of a function is any input value that causes both the numerator and the denominator of a function to be equal to 0. So any factor in your function that causes both top and the bottom of your rational function equal to 0 is called a whole or removable discontinuity. We will talk about this more later. To find the vertical asymptote of a rational function, you just need to set the denominator of your function equal to 0 and then solve for x. Just keep in mind that a vertical asymptote can never be passed by the graph of your function. For example, if this is a vertical asymptote, my graph can never pass this point. It can get close, but never can pass this point. So a vertical asymptote can never be passed. Now let's try to find some of the vertical asymptotes of these functions. In order to find the vertical asymptote of this function, the first thing is to factor this function. Since we want to find a vertical asymptote which is only on the bottom of this function, I'm just going to factor the bottom at this point, and I'm not just going to touch the top because I don't need it at this point. So to factor this polynomial, we can use the big X. On top goes 2 times 3, which is 6. The bottom is 5. Two numbers that multiply by 6 and add up by 5 could be 2 and 3. Since the a value of my polynomial is not 1, then I have to use the grouping method. So I'm going to keep the first term and then split the second term using these two numbers. Like 5x will be 2x plus 3x. And then the last term will just be written here. Now I have two groups. From each group I'm going to factor the common factor. So between these two, 2x is in common. I will have 2x squared divided by 2x is x, and 2x divided by 2x is 1. And from the second group, we can factor the 3 out. So 3x divided by 3 is x, 3 divided by 3 is 1. Now in this polynomial, in each group we have x plus 1 in common in both of them. So we can factor x plus 1. And we will have 2x plus 3 left. So the bottom of this function is x plus 1 times 2x plus 3. Now I just need to set this equal to 0. So I'm going to set that equal to 0 and try to solve for x. Because my polynomial is in factored form, we can set each factor equal to 0 to solve for x. So x is equal to -1 here, and the second one, 2x plus 3 equal to 0. So we subtract 3 from both sides. Then 2x is equal to -3. Then divide by 2. From here, x will be equal to -3 divided by 2. So we have two asymptotes. One is negative 1, the other one is negative 3 over 2. We can also find the vertical asymptote of this one. We just need to set the denominator of this function equal to 0. X to the power of 4 is equal to 0. Now we need to solve for x. We can just take the fourth root of both sides. These two will go away and x will be cube root of 0, which is just 0. So this is my vertical asymptote here. And these two were the vertical asymptotes of this function. Now let's see how we can find the horizontal asymptote. Before that, keep in mind that any horizontal asymptote may be passed by the graph. For example, here, this is my coordinate plane, and I have two vertical asymptotes and one horizontal asymptote like this. It is possible for my function to pass this horizontal asymptote. For example, my function could be like this: one curve here, one curve here, and one curve like this. So as you see, this is passing the horizontal asymptotes, and this is possible. But the vertical asymptotes are never passed. So this was about the horizontal asymptote. Now we'll see how to find this. To find the horizontal asymptote of a rational function, we need to consider the term with the highest degree of the top and the term with the highest degree of the bottom. And then we need to find the degree of the top and the degree of the bottom from that. So we're going to call the n and d as the degree of top and degree of bottom of the function. Once we have n and d, we're going to compare these two together. If the value of n is greater than d, like the top is higher than the bottom, this means top is heavier, then there is no horizontal asymptote. We need to look for slant asymptote. An example of such a function which has top heavier than the bottom could be, let's say, x squared minus 3 divided by 2x. So here the degree of top is 2 and degree of the bottom is 1. So n over d is 2 over 1. The top is heavier than the bottom, so this means we don't have any horizontal asymptote. What if the degree of top and the bottom are equal to each other? In this case, the horizontal asymptote will be y equal to leading coefficient of top over leading coefficient of bottom. For example, I have 4x to the 2 minus 3x on top and 2x squared plus 4 in the bottom. The degree of top is 2, degree of the bottom is also 2. So n over d here is 2 over 2. So both of them are equal to each other. Now I can find my horizontal asymptote. The horizontal asymptote is the leading coefficient of top, which is 4, over leading coefficient of the bottom, which is 2. And 4 divided by 2 is 2. So this is the horizontal asymptote that we have here. Now, if the bottom is heavier than the top, for example, I have, let's say, x minus 3 over 2x to 4 plus 2. The Degree of the top is 1 and degree of the bottom is 4. So n over d is 1 over 4. This means the bottom is heavier than the top. In such a case, the horizontal asymptote is just y equal to 0, and we don't need to do any operations. Let's do one example here. To find the horizontal asymptote of this function, we need to find n over d. Degree of top is 2, and degree of the bottom is again 2. So this means the horizontal asymptote will be leading coefficient of top over leading coefficient of bottom. That will be 8 over 2. Notice that here I didn't use the factored form of my function. I just use the original. It's easier if you use the original function and not factored form to find the horizontal asymptote. To find a vertical asymptote, we need to factor the bottom, but for horizontal asymptote, just use the original function, which is not factored form. The second example, n over d, degree of top is 3 and degree of the bottom is 4. So this is bottom heavier. In this case, horizontal asymptote is just y equal to 0. So this is the horizontal asymptote. Now we want to learn how to find the removable discontinuity of a rational function. As we said at the beginning of the lesson, if there is a factor in our function that makes both the top and the bottom of the function equal to 0, that is a removable discontinuity. So basically, if a factor cancels both on top and the bottom from both top and the bottom of the function, then there is a removable discontinuity or hole in the graph of the function. So let's see how does that look like in a function. I'm going to start by factoring this graph, this function. X squared minus 4 is difference between two squares, two perfect squares. So we can use this formula, this rule. A squared minus b squared is a minus b times a plus b. So x squared minus 4 will be x minus 2 times x plus 2. At the bottom we had x minus 2. Now we see that there is a factor both on top and the bottom. This is the common factor, and we can easily cancel these out. Both of these factors are the factors that can make the top and the bottom equal to 0 if the x value is equal to 2. So in order to find the removable discontinuity or the whole of the function, you just need to figure out what value makes this factor equal to 0 and causes both top and the bottom of your function equal to 0. So to find the x value of the removable discontinuity, let's just go back here and write some notes first. Okay, to find the x value of the removable discontinuity, we just need to set the cancelled factor equal to 0 and solve for x. And to find the y value of that, we need to plug in the x value in remained function and solve for y. So here, as I cancel these two factors, the remained function will be x plus 2. So this is my remained function. Let's first of all find the x value of removable discontinuity. To find the x of this removable discontinuity, you set the cancelled factor, which was x minus 2, equal to 0, and solve for x. So x of removable discontinuity will be 2. And then we need to plug in this value into the remain function and solve for y. So y is x plus 2, and we plug in these 2 for x, which will be 2 plus 2, which is 4. So y value of removable discontinuity is 4. So this is my removable discontinuity, 2 and 4. We will graph this later over here. Before that, let's start graphing the remain function. Once you cancel the common factor and you have the remain function, this remain function is what you are going to graph. We are not going to graph the original function, just the remain function. So now it's time to graph y equal to x plus 2. As you see, this is just a linear function, and graphing this would be very easy for us. We can just find the x-intercept. X-intercept can be found when you set the y equal to 0. So x plus 2 is my y equal to 0, and from here x equal to negative 2. So negative 2 and 0 is the x-intercept. To find the y-intercept, you need to set x equal to 0 and plug into your remain function. So y will be 0 plus 2, which is 2. The y-intercept is 0 and 2. Now we are ready to graph our function because we have all the information, y-intercept, x-intercept, and the removable discontinuity. And we don't have any vertical horizontal asymptote because, as you see, this remain function is just a slant linear function, and it doesn't have any vertical or horizontal asymptote. So we can start graphing. X-intercept is at negative 2 and 0 here. Y-intercept is at 0 and 2 here. And the whole of the function is at 2 and 4. 1, 2, 3, 4. So it's going to be somewhere around here. I show this with an open circle because it's a hole here, a removable discontinuity, and we have to show that this was a hole on our function. So then we just need to connect the lines and make sure keep the rest of the function, graph the rest of the function over here like this. So keep this open circle just empty. Now let's graph this function. This function is already factored. We just need to see if there is any common factor that can be cancelled from both top and the bottom, and that is x minus 5. So we cancel this, and the remain function, from the top we have only 1, and the bottom is x plus 2. This is the remain function. Now we need to find the removable discontinuity. You set the x minus 5, the cancelled factor, equal to 0, and solve for x. X equal to 5 is the x value of removable discontinuity. And then plug this into the remain function. Y will be 1 over 5 plus 2, which is 1 over 7. This is the y of removable discontinuity. So removable discontinuity is 5 and 1 over 7. Then we need to graph the remain function. Graph the remain function, which is 1 over x plus 2. We need to find the x and y intercept. First of all, x-intercept. For x-intercept, we know that we need to set y equal to 0. And in a rational function, if the whole rational function is equal to 0, that means the top equal to 0. So this is 1 on the top, we set that equal to 0, but it's not equal, 1 is not equal to 0, that means there is no x-intercept. To find the y-intercept, set x equal to 0 and plug into the remain function. So y will be 1 over 0 plus 2, and it's 1 over 2. This is the y-intercept. It's 0 and 1 over 2. Then let's find the vertical asymptote. To find the vertical asymptote, we need to set the bottom equal to 0. So x plus 2 equal to 0. Solve for x. X will be equal to negative 2. Horizontal asymptote. We need n over d. Degree of top is 0 because if you have a constant number, that constant is actually 1 times x to the power of 0. So the degree of top here is 0. So it's 0 over the degree of the bottom is 1. N over d is 0 over 1. This means that bottom of the function is heavier than the top. So the horizontal asymptote will be just y equal to 0. Now we have all the information. Y equal to 0, horizontal asymptote, vertical asymptote, y-intercept, no x-intercept we have here, and we also have the whole of the function. We can start by finding the vertical and horizontal asymptote. Vertical asymptote was at x equal to negative 2. I already draw this for you. The horizontal asymptote was at y equal to 0. So y equal to 0 is the horizontal asymptote that we have. It's this line. Now we find the y-intercept, which is at 0 and 1 over 2. So let's say this is 1. This point will be 1 over 2. This is the y-intercept. No x-intercept we have here, and we find 5 over 1 over 7, 5 and 1 over 7. 1, 2, 3, 4, 5. So this is 5, and the y value is 1 over 7. It's going to be a point very close to 0. I'm going to show that with an open circle because it's the removable discontinuity. Now we can start graphing the function. On this side, because we already have the points here, we know that the graph is going to pass through these points. So it's going to be something like this, passing these 2 points. But the other part of the function, we know that the rational function has 2 sides, 2 parts actually. But sometimes these parts are like these, sometimes are in this way, or even in this way. So there are different ways to put these curves. Here we already have this one, but we don't know if the other one is going to be here on top or the bottom. In order to figure out where to put that part of the function, we just need to find one point in this area and plug into the remain function. So we know that here is x equal to negative 2. We're going to find a point before x negative 2. Let's just find negative 3. And we plug into the remain function. 1 over negative 3 plus 2. It will be 1 over negative 1, which is negative 1. So when x is negative 3, y is negative 1. It's going to be somewhere like this. Now I know that my function is on this side and not on the top side of the horizontal asymptote. We can easily graph this function in this way. So this is the graph of this rational function. Now we're going to graph this one. The first thing is to factor the function. because we want to know if we have any hole in our function or not. So we need to look for canceling factors. If we factor these, negative 4 on top, negative 3 in the bottom, the two numbers will be 1 and negative 4. So we factor this as x plus 1 and x minus 4. And the bottom is x minus 4. Now we can cancel these two, and the remaining function is x plus 1. Find the removable discontinuity first. X minus 4, the cancel factor, set that equal to 0, x is equal to 4. X of removable discontinuity is 4. Then we put this in the remain function. This is our remain function. So y will be 4 plus 1, which is 5. So removable discontinuity is 4 and 5. Okay. This is our removable discontinuity. Now we need to find the graph of the function. We need to graph the remain function. Graph y equal to x plus 1. We just need 2 points. X-intercept, set the y equal to 0, so this will be 0 equal to x plus 1 and x is negative 1. And find the y-intercept, set x equal to 0, plug into the remain function, y will be 0 plus 1. X-intercept is negative 1 and 0, y-intercept is 0 and 1. We start graphing them. 0 and 1 is my y-intercept, negative 1 and 0 is x-intercept, and the whole is 4 and 5. So it's going to be 1, 2, 3, 4, and this is 4, and we go 5 up, 1, 2, 3, 4, and 5. So it's going to be somewhere around here, and we show that by an open circle. Now we can graph the function by connecting these lines, and make sure you keep this side, like the whole of your function, not covered. It should be an open circle. So this is the graph of function here. Now let's find the graph of this one. Again, the first thing is to factor top and the bottom. For the top, negative 8 goes here, 2 goes here. The two numbers could be 2 and 4. We make the two negative, so multiply will be negative 8 and add them will be 2. So this is x minus 2 times x plus 4. Factor the bottom now. The top is 4, bottom is 5. The two numbers are 1 and 4. The factored form is x plus 1 and x plus 4. Now we see that we have a cancel factor. This time the remain function is x minus 2 over x plus 1. It's a rational function. Find the removable discontinuity first. X plus 4 equal to 0, then x is equal to negative 4. And then plug this into the remain function. Y will be negative 4 minus 2 over negative 4 plus 1. This is negative 6 over negative 3, which is 2. So removable discontinuity is negative 4 and 2. Now we start graphing the remain function. Graph y equal to x minus 2 over x plus 1. We start by finding x and y-intercept. X-intercept, set the top equal to 0. So x minus 2 equal to 0, and from here x is equal to 2. To find the y-intercept, you set x equal to 0 and plug here into function. Y will be 0 minus 2, 0 plus 1, which is negative 2. X-intercept is 2 and 0, y-intercept is 0 and negative 2. 0 and negative 2. Vertical asymptote. We set the bottom equal to 0, x plus 1 equal to 0, and solve for x. X will be negative 1. Horizontal asymptote. Find the degree of top. Degree of top is 1. Degree of the bottom is also 1. So n over d is 1 over 1. Top and the bottom are equal to each other. So the horizontal asymptote will be leading coefficient of top, which is 1, over leading coefficient of the bottom. So this will be 1 over 1. The leading coefficient of top is this 1. The bottom is 1. These are the coefficients of the term with the highest degree. So this is 1. Y equal to 1 is our horizontal asymptote, vertical asymptote, and we have the whole x and y intercept and all the asymptotes. We can easily graph the function now. The horizontal asymptote was at y equal to 1. Vertical asymptote is at x equal to negative 1. Now, the x-intercept is at 2 and 0, y-intercept 0 and negative 2, and the whole of the function is at negative 2, negative 4 and 2. 1, 2, 3, 4, and 2 is going to be here, open circle. Now we can easily graph the function. Luckily here, we have points on both sides of the asymptote. So I know one of the curves of the graph will be here and the other one here, because we have a removable discontinuity on this side. That means the graph was here. So this is the graph of function. The last thing that I want to talk about is the domain of this function. We know that if we want to find the domain of a function, we just need to exclude the vertical asymptote. But here we also have a hole, which is the discontinuity of the function. So we can write the domain of the function is, as I move from left to the right, because I have a hole here, I have to make a jump at this point. So it starts from negative infinity, and at negative 4 we have to make a jump and go after the negative 4. So this will be negative 4, 2, and then I can just continue moving. As I reach to the vertical asymptote, which is x equal to negative 1, my function again is not defined here. So at negative 1, I have to make another jump and go to after negative 1. And after that point, we can continue forever. So this will be the domain of my function. Make sure you practice on homework. The only way to remember everything is to practice more. You will be really master in graphing your function if you practice. Have a great day.